talking about temperature. I think some more about temperature. Temperature is one of the things that you guys have been recording. And this chapter almost kind of reminds me of if you're looking for a place in the world to relocate and you're looking for that specific temperature, then you might get some ideas here. Okay. So here in the Midwest, though, our temperature, it has a great swing. Okay, because our summers are hot and our winters are cold. And actually, here in the Midwest or in Kansas, if you're in the middle of a landmass, actually you're going to get those temperature swings. Okay, if you're on the coast, maybe some of you guys know this, but your temperature swings throughout the year are less. Okay, so you guys, you might have been born into it, but this is kind of what you got here in Iowa. Okay, kind of an assortment of temperatures. Okay, so one of the things we need to talk about is numbers. So anytime you see the word mean, I want you to think average if you didn't already. Okay, so the word mean is average. And you guys probably know if you had, for instance, 5 values you wanted to average, you would add the 5 values together and divide by 5. Okay, and that's kind of exactly what they do with regard to getting the average daily temperatures. So daily mean means it's the same thing as daily average. You do have a couple of choices. You could either go ahead and take the temperature on the hour, and that'll give you 24 temperatures, and then divide by 24. Or for the given day, you can go with the max and the min, and then divide by 2. Okay, so that's a possibility. We're going to talk about kind of temperature ranges, and anytime you talk about temperature range, it's always just the difference between the high and the low. What's the temperature range? Okay, and that's the swing. What's the temperature swing? What's the temperature range? Is it little? Okay, do you have not much temperature swing, or do you have a big temperature swing? Okay, all right. So the monthly average or the monthly mean, it depends on how many days you have in that month, but basically you take the average temperature for each day, you add them together, and you divide by the number of days, right? Not too bad. Well, what if you have a location and you want to know for that location, this to me sounds like a stretch, like Keokuk, Iowa, what is the temperature? I mean, like, what is the average temperature? Yeah, I know we can look at what the current temperature is, but what is, like, throughout the year, the average temperature? So what you do then is revisit for that location the 12 monthly temperatures. You add them together and divide by 12. Okay. And we are going to be looking at some climatograms. I think we looked at one before maybe. Climatogram basically goes from January to December. And so we're going to actually be able to kind of look at the graph and see what kind of temperature swing, temperature swing a location has. So to me, that makes more sense. What is the annual temperature range for a location? Well, in this case, again, you go back to the months. You take the high month, and from that you subtract the low month. So that's kind of the swing. All right, so some extreme temperatures. I don't know, but I'm kind of liking this weather outside. No? Oh.
But yesterday was.
I'm ready for summer.
You're ready for summer? Warmer even, right? But you don't want cold, right? You don't want any colder than this.
I mean, if we get snow, it better be a snow day.
If we're going to have snow, let's make it worth it, yeah.
I think it'd be cool to have one huge snow, and then I'm good with
Yep.
it.
Yeah, maybe. A snow, because right when it snows, that's the most beautiful part, the whole white.
We're seeing the big
When it
flakes coming
sticks
in.
around.
The
you
big
see
flakes,
it.
yeah. So we'll see what we can do.
Yeah. The storm track would have to ship like 200 miles out of the south coast.
Yeah, I don't think this next storm, I think we're going to get mostly rain.
Yeah.
But do you know what tomorrow is?
Groundhog Day.
Groundhog Day.
Anniversary of that blizzard that happened in 11.
Oh, yeah, there was a nasty one came through Groundhog Day, yeah. So we'll just see. I think we'll be fine. It'll be here before we know. Well, hot summer, right? The hottest temperature in North America was 134 Fahrenheit in 1913. Worldwide, it's just a little bit hotter than that, 136. How about cold? The coldest temperature in North America was in Canada, minus 81 degrees Fahrenheit.
Oh my goodness.
Would you like instantly die?
Like instant frostbite as soon as
not
you
good.
walked outside.
That's not good, yeah. So, yeah. But worldwide was quite a bit colder than that. In the southern hemisphere, at the Antarctic, okay, minus 129 degrees Fahrenheit. That's not right. That's just not good.
Imagine if the heater went out. Oof, be cold.
It would be bad. It would be bad. I agree.
I think you'd lose functioning of your body. I think you.
Yeah, I think that's dangerous temperatures, with or without the wind, yeah. So these actually, we're going to talk in, this is another weather map, and these are talking about temperature. These are contour lines. You can kind of see the lines on here, contour lines. These contour lines are connecting locations with actually that are 20 degrees Celsius, or excuse me, is that right? Fahrenheit, 20 degrees Fahrenheit, final answer.
If it's 20 degrees Celsius. it'd be-
I know. Okay, and let's go out one contour line. This contour line is connecting locations that are 30 Fahrenheit. This one, okay, 40 Fahrenheit. Okay. They are, if you've ever done much with like elevation, like an elevation map, a lot of times you'll kind of see these contour lines drawn to show you locations with the same elevation. It's the same idea. Okay. So, yeah. So what temperature do you think we kind of are? We're straddling kind of. Maybe right here.
I say, dude,
Only between 40 and 50.
Well, we're kind of between, I'm kind of thinking 50 and 60 maybe. Or you think we might be on the other side of it? We might be.
I think I made 53.
I think it's like
Maybe
54
like-
point something, because it's almost 55.
You think,
Yeah, it could be
Yeah.
54.
yeah, that's true. She's kind of looking at this one's 55. Maybe 50, 51 to 54, somewhere in there. Degrees Fahrenheit. Cool. Yep, very good. So I like what your author's done. Isn't this neat? Like this kind of finger stuff over here, actually you can see that these two are the same maps. Okay, so this one is just color coded and this one has the actual contour lines. So I think that's neat. So we're actually going to be switching it up in the next unit and looking at contour lines, again, not connecting locations with the same temperature, but connecting locations with the same pressure. Okay? If, like this, they're connecting the same temperature, we call those lines, contour lines, isotherms. So that's an iso means the same, so those are isotherms. Yep. Now here's one for you. Can you see where if you were going to go from Las Vegas to Guadalupe, okay, check out the crazy temperature path you would be on, okay? Your temperature changes quite a bit, right? And actually kind of what you're looking at is you didn't have to go very far to get a new isotherm. You didn't have to go very far to get kind of the next 10 of temperature. These tight things, closely spaced isotherms, means temperature changes quickly. Okay? Makes sense. Temperature changes quickly.
Usually means like mountain ranges or.
Yeah, and it varies because you could have air masses too. It's not just not topography, but it could be. And so kind of like here, if you're going to go from Des Moines to Topeka, right? You know, that temperature change is pretty boring.
Yeah.
Kind of less drastic. And one of the things about temperature changes, though, is that if the temperature does change pretty drastically, you have a steep temperature gradient, then probably you're going to have some sort of wind going on with that too. So, we got in the last couple of cars, I think I bought. We have a thermometer in our car. So one of the things, if you're like me, especially when it's precipitating, you watch your thermometer. You're like, is it going to be rain or snow, right? But next time you're watching your thermometer, think, oh, I just crossed an isotherm, okay, when it gets warmer or colder. Right? Okay. So this is actually 5 different locations. This is a climatogram, and we are going to be looking at a few of these. Like I said, I think we looked at some before. Along the x-axis are months. So here we have January, February, March, April, May, June, etc. You know, this ends up with November and December. Okay, so those are months. And there are 4 different locations here. Here we have, let's see, You guys would tell me it's the hottest near the equator. Kind of the title of this slide is what's the effect of how close you are to the equator. Of course, we call that latitude. So if we pick on something that's kind of close to the equator, it's that purple line. Okay. Now, can you see where there's not much change throughout the year? Okay. The range, you know, for living near the equator, actually you kind of have a relatively constant temperature. Okay. So that's 4 degrees. And then if we go 39 degrees, oops, yeah. And then if we go 50 degrees, and then we go 71 degrees. Okay. So this is 1, 2, 3. That's the blue line. It's 3, and the black line is 4. Okay. They actually do pretty good. They kind of have a hump, and then a hump, and then a hump. But of course, as you go up in latitude, you guys tells me it gets colder. So this one is the highest latitude. Okay. 71 degrees north latitude throughout the year. What I think is kind of interesting is if you were to take like the range for this location in Alaska, it's to me kind of similar to the blue line, which is in Manitoba. Okay, so that's the range we're talking about. But definitely colder down here, warmer near the equator. I was just looking at this just now, and I'll circle it with blue, but do you see the one in the southern hemisphere? The green dude? Okay. So here, when we are experiencing, and we talked about this before, and you guys knew this before you came to the class, but here, things in the southern hemisphere have opposite temperatures. So June and July is its coldest temperature.
St. Louis and Cape Town are about the same distance from the equator. How come St. Louis is such a bigger hub?
Temperature range?
Yeah.
I think we're going to see that might be the effect of, I don't know, if it's ocean current, maybe? That's a good question. Yeah, they are similar, aren't they? Oh, I know the other thing. Have we talked about the urban island heat effect in here yet? Basically, cities are warmer. And it could be that St. Louis, yeah, has that kind of going for it. So that's a good question. It's interesting, climatic grams. But this is kind of the effect of latitude, kind of how close or how far it is from the equator. So aside from latitude, we're actually going to step through each of these 5 and say, if you live somewhere else, what other things can affect your temperatures? Now, we're definitely later on going to talk about air masses, because we've talked a little bit about air masses now. You can have a warm air mass come and make you warmer, artificially warmer. You can have a cold air mass kind of settle into Canada and move down, okay, and make you artificially colder. But these are just kind of, these aren't air masses. So we'll kind of talk through each one of these, starting with the first one. Okay, so the deal is, if you have a location that is, there's words for these, okay, continental, okay, that means that you're in the middle of a landmass. If you have a location that is marine, that means you're on the coast. Sometimes marine, you'll hear me kind of slip into a term that I'm sure makes sense to you. Sometimes I'll call it coastal. Coastal and marine are the same thing, a coastal location, a marine location. It's just basically on a large body of water, okay, on the edge of a continent. Sometimes continental, I'll use the word inland, same thing, inland or continental. So you would probably call us inland right now. Okay, that's us. So the thing about if you are on the coast, okay, let's go ahead and pick somewhere here. If you're either here or here, and of course we have the Pacific Ocean over here. Large bodies of water, and I'll kind of talk about why this is, but large bodies of water are very stubborn. Okay, they're stubborn in 2 ways. Large bodies of water are stubborn to heat up, and large bodies of water are stubborn to cool down. So if they're stubborn, in this case in May, to heat up, you figure May, you're starting to kind of segue from spring into summer, okay? So actually what this is showing you is, can you see where the landmass, California, is hotter, okay? Because remember, we're going to get a better angle in May. We're just going to get more energy from the sun. We're, like I said, we're going towards summer. Okay, so the land will heat up quickly, but the water lags behind. And so that's kind of what we have going. And I will tell you that if you are a maritime location, maybe you already know this, if you are a maritime marine coastal location, okay, you are going to benefit from that body of water being stubborn. Okay? So we'll kind of see that in some climatograms here in a minute. But why is water stubborn? Why are the oceans stubborn, delayed in heating up and delayed in cooling down? So this means actually kind of in about, let's see, fall, so August, September, October, this means that the oceans actually can retain their heat, which is true. Okay. Well, there's a few reasons. One is that water can move, I guess, as compared to soil. If you've ever heard around here, like the soil is frost, like just like 4 inches, and then it's warm underneath that. Okay. The other thing is that water is transparent compared to soil. So, like that radiant energy can actually shine down into the water and get down into it. Another reason, I'm going to have a few slides kind of talking about this, but let's see, how do I say? There's a good example. So, like if you have 2 pots, and you have a pot with a plastic handle, or a pot that has the metal handle, basically it's the pot extended out, okay? Which one of it are you going to want, which one of it will protect your hand better? The plastic, exactly. Now this is kind of, there are a few things about plastic, so maybe it's not a good example, but the energy won't, we said, conduct up, okay, as well from the plastic. It kind of, but the other thing about plastic is it has a little bit lower specific heat. It takes more energy for it to heat up, okay? And so the thing about water, I'm going to kind of show you, put this in perspective, but water, basically, you have to hit it with a lot of energy to get it to budge in temperature. Okay, so it's stubborn with regard to specific heat. It's like a thermal property. Okay, so they're actually, how stubborn is water to heat up? There's actually a word for that property called the specific property of a substance. And I kind of explain it like this: the specific property of any substance, and you can look up the specific heat of anything you'd be curious about. But basically, what I'm kind of describing in my notes is you take 1 gram of that substance, and you zap it with energy. So here's my E for energy, okay? And what I'm trying to do in my little experiment with specific heat is I'm trying to raise its temperature from, I think it's 13.5 degrees Celsius up 1 degree Celsius, so 13.5 to 14.5 degrees Celsius, okay? So the specific heat basically is the amount of energy that you need to hit 1 gram of material in order to accomplish that temperature change. That's specific heat. Easy for me to say. So we have, water has a high specific heat. Now something that has a relatively low specific heat would be the geosphere. And soil is different. If you take sandy soil, if you take 1 gram of sandy soil, and we're going to see an example here in a minute, 1 gram of sandy soil, you'd have to zap it with 0.8 joules of energy to get it to budge its temperature 1 degree Celsius. If we compare that to 1 gram of water, the specific heat of water is 4.18. So you would have to take 1 gram of water, and you'd have to zap it, not 0.8, but you'd have to zap it with 4.18, okay? So it just takes a lot more energy to get it to budge just 1 degree Celsius. And the reason is that's just kind of a thermal property of sandy soil versus water, okay? And you've run into this before, because like if you've ever want to go swimming and you have to basically cross a beach to get to your swimming area, and the sun's been shining, that sand can be very hot. Okay, it's really hot.
Wayland area, it's really sandy.
Okay,
Near the rivers.
it's very hot. But then your water can be, normal temperature, but the sand heats up very quickly. Yes.
Okay, so we're talking about that. So I'm at a lake, the sand's hot, but the water is like bath water. So you're saying that even though the sand's super hot, the water still feels like bath water.
Interesting. The lake, if depends on what time of year it is. If it was like kind of fall, and if it was a big lake, it could actually kind of be
it's
retaining.
Big. It's really deep too.
Okay, it could be retaining some of its heat from it picked up during the summertime.
Well, we're trying.
So.
I don't know. I think there's like a spring.
Oh
Okay.
yeah. Oh my gosh. Yeah. Now that's a different phenomenon. It's if it's warm water being fed through like a kind of a thermal sort of spring. Yeah, that's possible.
Yeah.
Sounds nice. Let's go.
It was 80 degrees in Tulsa. This last weekend it was 80. I was like,
Wow.
and I'm here.
What am I doing here? I know. Well, some of us are just stuck here. But see, you guys are young and you can pick where you want to go after this. So, assuming they're at the same temperature to kind of show you like the differences between the specific heat of water versus soily sand, if they start at 10 degrees Celsius and you zap them, like this says, with 4,190 joules of energy, what you're going to see is that your water is only going to budge 1 degree, but your sand is going to go up a lot more than that. Okay, so with the same amount of energy, the one with the higher specific heat, which is water, only went up 1 degree. Your sand is going to go up, 5.24 degrees.
Okay. It still doesn't make sense. Like, it was. I came back for fall break and it was hot.
Are you still thinking about your lake and stuff? I do think that you might have a hot spring. It's being fed by a hot spring.
I mean, because the Arkansas River runs into the lake. We have a big dam.
Okay.
Kind of. I mean, it's not as big as
know.
the one here, but it's pretty good size.
Well, there might be some other clues in here, so we'll have to see if anything else. I'd have to see
I'm
it.
curious now.
And last but not least, this is actually why water is so stubborn to heat up or cool down. It actually has this other phenomenon going on, where if you're talking about heating up water, if you heat up water, you're going to have more water liquid particles evaporate, go into their gaseous state. And as they do that, and we'll talk more about this in the next unit, basically one of the things we talked about is to go from an L to a G, you need energy, right? E, required or absorbed. Energy is absorbed to go from a liquid to a gas. Okay? And that energy that's absorbed actually has a cooling effect on the water. So that's one more thing going on in one direction. Okay. So that was all just to say. Now, I like what your author's done is he basically looks at that one effect, in this case kind of the maritime or marine location versus continental location, and he throws it up, he picks two locations, one that fits both bills, and puts it up on a climatogram to compare them. So let's see, I bet you guys would tell me Winnipeg is continental. Okay, so here's Winnipeg. And then Vancouver is an example of maritime or marine. And here's Vancouver. Okay, so a few things, but if you were to compare kind of the range, so let's pick on Winnipeg first. It's the blue line. The range is like this, okay, versus the Vancouver is like this. Okay, so of course the one on the coast has a lot smaller range. And would you say, too, like the Winnipeg one, it's June and July, it's hotter. And then, of course, January, December, it's colder. And that's because the ocean, the effect of the ocean. Let's go. So just a few more things about the ocean. We said that most of the Earth is actually covered by large bodies of water, but it's not the same in both hemispheres. So what you're doing is you're looking, in the north hemisphere, you're looking down, okay, from the North Pole. In the southern hemisphere, you're looking down from the South Pole. And look at all this water. Okay, so the southern hemisphere has it going for the lion's share of large bodies of water. So you would expect the southern hemisphere actually to have kind of more of the kind of cushioning of water. So let's look at the southern hemisphere and compare it to the northern hemisphere. And what you do, for instance, we could take 60 degrees latitude in the northern hemisphere and in the southern hemisphere. What these are is the temperature range. What is the swing? Okay, notice where you have more water, the temperature range in general, at that latitude, at 60 degrees latitude in either hemisphere, you're going to get a 30-degree temperature swing in the northern hemisphere and only an 11-degree temperature swing in the southern hemisphere because it has more water. But now, if you're like me, one thing I don't like about that is it's like, what latitude did I say? The 40 degrees or whatever?
I think it's 60.
60, okay, thanks. So you're like, really? So 60, man, it gets, so this is 90 up here, and this is the equator. I wish they had a C, but yeah, there's the equator. Right here, okay, that works. Okay, so 60 is about here, and they're just, I mean, how can you really draw, I mean, so that would be 60 degrees, I guess. They just spit back one temperature, or actually annual temperature range throughout the year. Compare that to, here it is. Yeah, goodness. I mean, there's a lot of water down there. So that makes sense. So here the temperature range. There's no place to live, though. That's problematic. Okay.
That's your thing.
I know. But the reason I brought this actually is the next topic. You guys already know this, that if you go, I'll put this whole thing up here. So if you go on our, which is warmer? If you go dip your toes in the Pacific or if you dip your toes in the Atlantic? The Atlantic is warmer, okay? And so honestly, which coast it is? Yeah, it is a lot warmer.
Really?
Yep. Road trip.
No, Pacific Coast, too many earthquakes.
So which coast you live on actually is a player into what your temperatures are going to be. And the way it works, and actually there's a really good figure from your textbook coming up. But let's find that. So over here we have basically a cold current right there. Okay, that makes us cold, and we have a warm current right here. Do you remember at the end of chapter 2, we ended with basically at the equator, throughout the year, they get extra energy. And we said the poles throughout the year, they're deficit. Okay, so we had surplus near the equator of energy throughout the year, a deficit at the poles, about 38 degrees latitude, it kind of crisscrossed. So oceans are great at bringing down cold and returning warm. They're great at kind of balancing things out. Oceans totally rock. Okay. So here's an example of our Atlantic Ocean and how we have that warm current. It's called the Gulf Stream current, kind of coming up to warm folks along our northeast. And here's a figure from your textbook. And what's that?
I noticed, it hits a certain point and there it kind of dips off. So like,
Right here?
yeah, where it hits kind of North Carolina area, it gets a little bit colder. Why isn't it shoot up?
I think does this make sense that actually this is kind of sourced down here. Let me pick a different color. This is sourced down near the equator, so it's nice and warm. Okay, and of course, as things are warm, as they get into things that are cooler, they start to cool off. But honestly, this is up here. Josh was asking, why is that cold? That's basically kind of a different it's not part of the warm. It's basically sitting up there. It's kind of a, let me see if
I would say a high pressure of water.
well, let's see what this says. See if we can look at this. So this figure, if we look in the same part of the world, this is right here. So this is the Gulf Stream. This is what we looked at before. And up here, kind of up here, the figure we looked at just a minute ago kind of showed it cold. I don't know. This isn't kind of showing the same thing we saw with that. So I don't know. But if we go up a little bit further, what I was saying is, you see up here, basically that's just kind of cold water that just is cold. It's limited with regard to the energy coming in, and it's just colder versus our Gulf Stream current is heated because it starts near the
cold's moving down.
Yeah, the cold would be moving down. So these different ocean basins. So we have north and south ocean basins, but the entire ocean basin is kind of connected with different currents, and the currents go to make a circle we call an ocean gyre. So maybe kind of what Josh was talking about. We're going to talk about, I'm going to put an H here. I'm going to kind of look ahead for a minute. What does the H stand for?
High pressure.
High pressure, exactly. There happens to be an H in all of these, in the center of all of these ocean gyres. Okay? They're a semi-permanent high, which means that semi-permanent means it's not always there, but it's kind of always there, semi-permanent high. One of the things about high, have you ever heard the go flush, if you're kidnapped and you don't know which hemisphere you're in, go flush the toilet and see which way it goes, yeah. And we'll talk about why that is, and it's actually a myth, but it's kind of cool. In the northern hemisphere around high pressures, airs go clockwise. Air goes clockwise and ocean currents go clockwise. Actually, ocean currents are only created by the wind that goes over them. So can you kind of see the clockwise there? We have a clockwise here. We have a clockwise here.
Is
Okay.
that why toilets flush opposite ways, or is it just because the?
It's because of how the porcelain is, kind of. The thing about, if your toilet, now this is kind of icky, but if your toilet was basically about the size of a city, which is kind of strange to think about, then you would have enough water to actually go ahead and make the case. Okay, but toilets don't have that much water, and they're kind of short-lived, usually, if they're working right. So what I've read, what most influences what direction they flow is kind of how they come out, the porcelain is, yeah. So
that's why it's backwards in Australia, because it's counterclockwise.
yeah, exactly. So there's something to be said for that. If you go down here in
Is
this,
that the Australian current that does that? Or what?
the thing that makes them go counterclockwise in the southern hemisphere is because they're in the southern, or clockwise, excuse me. Did I do that wrong?
It's
Yeah, counterclockwise, yeah. The thing that makes it go counterclockwise in the southern hemisphere is because it's the southern hemisphere.
So if I went to Brazil and used the restroom, it would be counterclockwise?
Well, according to the myth, yes.
Okay.
But it's not really right, because it's not big enough. The flow isn't big enough. But that's kind of what people think, and it's kind of interesting to think that, because there is something to be said
Yeah,
about
'cause there's Australia, you can...
Mythbusters. We'll have to post that.
So when the Pilgrims were coming across from England, they were fighting the current the whole way.
The Pilgrims were hoping to catch a wind, and we'll talk about the prevailing easterly trade winds they were hoping to catch, yeah. So, but that's a good one too. Okay. So all of this, after all that talk, remember some currents are warm and some currents are cold. Good discussion though. And so actually it works out pretty good where continents, this is actually a continent in the southern hemisphere. This is South America. And it's set up just like North America. So remember we said the Pacific Ocean is cold and the Atlantic Ocean is warm. Same diff down here. Even though the currents are going, the ocean gyres are generally going counterclockwise. It still works out that way because it's coming from them. Okay? So if we pick on the one on the cold side, on the west side, okay, that's Peru, okay. Oh, sorry, not Peru. That's the Peruvian current we'll be talking more about. That's the Arica, okay. Not so surprising, throughout the year it's colder, okay. The one on the warm side, not so surprising, throughout the year it's warmer. Rio de Janeiro, hello. I just want to go, maybe. But what would you say about their temperature ranges? They look similar to me, yeah. They look like if you kind of go like his, very similar temperature ranges. So they both have the oceans that are kind of helping them to kind of hold a constant temperature, a small temperature range, but one's warm, one's cold. Hey, somebody's got to live everywhere, right? Something like that.
It's pretty.
It is very pretty. And seeing that snow-capped mountain, you'd be like, okay, snow-capped, I bet it's kind of, away from the equator. But this is actually 3 degrees away from the equator. So one of the things you guys already know is that if you go up in a mountain, it gets colder. That's what this is kind of emphasizing. Yeah, elevation. Remember, elevation and altitude are the same thing.
Well, we went hiking at my old school. We did a team hiking trip, and it was at least 5 or 6 degrees colder because we went into
Really?
Wichita Mountains. It's scary. Like, you have to watch out for rattlesnakes and stuff, but it was really pretty.
How old were you when you went on this field trip?
Huh?
How old were you?
Oh, it was last year.
Okay, good. I was like taking like fifth graders on a,
Oh, no, they
okay.
wouldn't do that.
Like, wow.
But it's so crazy there. They have a rattlesnake festival. It's crazy.
Rattlesnakes.
Yeah.
Tarantulas are big down there too.
Tarantulas and rattlesnakes?
Bother me.
You mean like there's like wild tarantulas? Or they
Yeah.
like them? Okay.
Yeah, no, they'll come in your dorm. They'll scare you. Plenty of scares.
Okay.
It's like, no mountain leaves the troposphere, does it?
Right. Yeah, I had to look that up one time because I'm like, because you know, after the troposphere is the stratosphere. Yeah.
We start getting warmer.
Yeah, because if you had a mountain that went into the next layer, it would start getting warmer as you go in the stratosphere. Yeah. Yeah, that would be crazy. But one of the things, this has nothing to do with this, but have you, like, those elevators that go take you to outer space?
Yeah.
They're not there yet, but.
That'd be really cool.
They could.
So 2 reasons why it gets colder when you climb a mountain. One is that you're getting farther from your heat, your source heat. Remember, the reason we have the temperatures we do usually is because the geosphere is kind of oozing energy. Okay, the geosphere. Here in the troposphere, Earth's surface is just basically kind of, and so the farther you go up a mountain, basically you're getting farther from kind of the main part of the radiator. But the other is that as you climb a mountain, the air gets thinner. We talked about that too, and so you have less gas particles basically to grab that radiation from the sun. Okay, so that's kind of both of those. So here is what your author picked. A couple of locations. They're both continental, I suppose. One is in the mountains. The La Paz is in the mountains, and the Concepcion is more like at the bottom of the mountains. Okay, so if we pick the mountain one first, okay, La Paz. So here is your mountain. Okay, so throughout the year compared to your sea level or whatever, okay, it's a lot colder. Okay. Again, though, what do you think about the temperature ranges? They're both continental locations. They're
Yeah.
kind of similar. I'm kind of surprised they don't have more of a temperature swing throughout the year. But maybe the scale is kind of different too.
Well, the Concepcion has a higher temperature extreme than La Paz, obviously because it's further away from the ocean. But
Yeah,
it
this
still falls
this
similar.
does look like a, yep, this would be more of a continental.
But it
or a
still
land
follows
one, yep.
Similar graphs.
Yeah, I agree. I think you can kind of see that. I agree.
Or
Okay.
at least it's more extreme. I mean, it might go the same temperature, but Concepcion seems to jump quicker, has a
Yeah.
higher slope.
Yeah, I agree. Well, why don't we hold the next topic for Wednesday?
Okay.
Yep. Kind of get a running start at it.
This is really getting into